On October 20, 2020, NASA's OSIRIS-REx spacecraft made history. After orbiting the near-Earth asteroid Bennu for 2 years, it descended to the surface. It touched down for just 6 seconds and collected a sample of regolith surface dust and rocks. On September 24, 2023, the sample capsule parachuted into the Utah desert. This marked the first time NASA had returned a sample from an asteroid since the Apollo era. The mission cost $1.16 billion. But the payoff has been incalculable. In 2025, after 18 months of painstaking analysis, NASA's Johnson Space Center and the University of Arizona released their final report on the Bennu sample. The findings sent shockwaves through the astrobiology community. The sample contained high-purity sodium magnesium phosphate mineral substances that can only form in liquid water. It also contained a cocktail of organic compounds, including amino acids, nucleobases, and polycyclic aromatic hydrocarbons. This is the first direct evidence that asteroids like Bennu carried both water and the building blocks of life to Earth, said Dr. Dante Lauretta. He is the OSIRIS-REx principal investigator and a planetary scientist at the University of Arizona. We've always suspected that life seeds came from space. But now we have proof. Bennu was a 4.5 billion-year-old cosmic delivery, and it may have brought life to our planet. The discovery of sodium magnesium phosphate in the Bennu sample was the first major breakthrough. This mineral is rare in the solar system. And it has a critical property: it can only crystallize in the presence of liquid water. For Na mg/Po to form, the temperature must be between 0 and 100 degrees Celsius. This is the range where water is liquid. The environment must also be neutral to slightly alkaline pH 7 to 8. This was a bombshell. Bennu is a carbonaceous chondrite asteroid. It is small, only 500 meters in diameter. It is dark and thought to be a leftover from the early solar system. Carbonaceous chondrites are known to contain water. But no one expected to find evidence of liquid water on Bennu. We were stunned when we saw the Na mg/Po crystals, said Dr. Lindsay Keller, a planetary scientist at NASA JSC. She is also the lead analyst for the Bennu sample. We used a transmission electron microscope to look at the sample. And there they were, tiny, needle-like crystals, each just 1 micrometer long. We ran X-ray diffraction tests to confirm their composition. The results were unambiguous: it was Na mg/Po. To understand how Na mg/Po formed on Bennu, the team turned to simulations. They modeled Bennu's history, starting with its formation 4.5 billion years ago. It formed in the outer solar system, beyond Jupiter's orbit, where water ice was abundant. They found that Bennu likely formed from fragments of a larger asteroid, one that was at least 100 kilometers in diameter. This larger asteroid, the team believes, had a subsurface ocean. Radioactive elements in its core generated heat. This melted ice into liquid water. Over millions of years, this water reacted with phosphate-rich rocks. It formed Na mg/Po crystals. When the larger asteroid collided with another object, it shattered into fragments. One of these fragments became Bennu. The Na mg/Po crystals are time capsules, Dr. Lauretta explained. They tell us that Bennu's parent asteroid had liquid water and ocean, even 4.5 billion years ago. That's remarkable because Earth's oceans didn't form until 100 million years after that. Bennu's parent asteroid was a water world long before Earth was. If the Na-mg-Po discovery was a bombshell, the finding of organic matter was a nuclear explosion. The team detected more than 20 different organic compounds. These included amino acids, the building blocks of proteins. The sample contained glycine, alanine, and serine. It also contained nucleobases, the building blocks of DNA and RNA. The team found adenine, guanine, and cytosine. They also found polycyclic aromatic hydrocarbons, or PAHs. PAHs are complex organic molecules that form in the atmospheres of stars and in supernovae. They are thought to be precursors to more complex compounds like amino acids. The amounts were small, just a few parts per million. But the implications were enormous. It meant that the building blocks of life were present on Bennu for 0.5 billion years ago. This is the closest we've ever come to proving the panspermia hypothesis, said Dr. Sarah Horst, an astrobiologist at Johns Hopkins University. Panspermia is the idea that life's building blocks, or even life itself, are transported between planets via asteroids, comets, or meteorites. The Bennu sample shows that asteroids carried both water and organic matter. Exactly what you need to start life. The team analyzed the isotopic composition of the organic compounds. Isotopes are versions of an element with different numbers of neutrons. For example, carbon has two stable isotopes, carbon-12 and carbon-13. The ratio of carbon-13 to carbon-12 is a fingerprint. It tells scientists where the organic matter formed. The Bennu organic compounds had a to the power of 1 cubed C value of -25 parts per thousand. Very similar to the power of 1 cubed C value of organic matter in ancient Earth rocks. This suggests that the organic matter on Bennu is the same type that existed on early Earth. It's not just that Bennu had organic matter, it's the right kind, Dr. Keller said. The isotopic match is too close to be a coincidence. This means that the organic matter on early Earth could have come from asteroids like Bennu. The OSIRIS-REx mission is not the only asteroid sample return mission in recent years. In 2019, Japan's Hayabusa 2 mission returned a sample from the asteroid Ryugu. Ryugu is another carbonaceous chondrite, similar in size and composition to Bennu. Comparing the Bennu and Ryugu samples has given scientists a unique window into the diversity of asteroids in the early solar system. The Ryugu sample, analyzed by JAXA and the University of Tokyo, also contained organic matter, including amino acids and PAHs. But there were key differences. Bennu's sample had a water content of 5% by weight, while Ryugu's was 3%. This suggests that Bennu's parent asteroid had more water than Ryugu's. Ryugu's sample contained no Na-mg-Po. This means that Ryugu's parent asteroid either did not have a subsurface ocean, or the ocean was not warm enough to form the mineral. Bennu's sample had more types of amino acids and nucleobases than Ryugu's. For example, Bennu had serine, while Ryugu did not. These differences suggest that not all carbonaceous chondrites are the same. Some, like Bennu, were formed in environments with liquid water and rich organic matter. Others, like Rygu, were not. This tells us that the early solar system was a patchwork of environments, said Dr. Tomoki Nakamura. Some regions had more water, some had more organic matter. Bennu came from a sweet spot, a region where the conditions were perfect for life's building blocks to form. The comparison also supports the idea that Earth received organic matter from multiple asteroids. It's not just Bennu or Ryeg, it's hundreds, thousands of asteroids, Dr. Horst said. Each asteroid brought a different mix of organic compounds and water. Together, they built up the inventory of life's building blocks on early Earth. The big question now is, could the organic matter from asteroids like Bennu have actually led to life on Earth? To answer this, scientists are conducting experiments to see if Bennu's organic compounds can form more complex molecules, like proteins or RNA, under conditions similar to early Earth. One experiment is being conducted at the University of Arizona's Lunar and Planetary Laboratory. Dr. Loretta's team is simulating the impact of an asteroid like Bennu on early Earth. They place samples of Bennu's organic matter in a high-pressure chamber. They heat it to 1000 degrees Celsius, the temperature of an asteroid impact. They add water to simulate Earth's early oceans. The results, published in 2025, were promising. The team found that the amino acids in Bennu's sample combined to form peptide short chains of amino acids. They also found that the nucleobases formed nucleotide building blocks of RNA. This is a critical step, Dr. Loretta said. We showed that asteroid impacts don't destroy organic matter, they process it. They turn simple organic compounds into more complex ones that are closer to life. Another experiment, at MIT, simulates early Earth's oceans. Dr. Jackie Lee mixed Bennu's organic compounds with salt water. She exposed the mixture to UV radiation to simulate the early sun. After 2 weeks, the pars had broken down into simpler organic compounds. The amino acids had formed longer peptides, some with 10 or more amino acids. These experiments show that Bennu's organic matter could have contributed to the origin of life, Dr. Lee said. It's not proof that life started this way, but it's strong evidence. The pieces are starting to fit. The success of OSIRIS-REx and Hayabusa 2 has paved the way for new asteroid sample return missions. NASA's Psyche mission, launched in 2022, is on its way to the asteroid Psyche, a metallic asteroid thought to be the core of a failed planet. The mission will not return a sample, but it will study Psyche's composition to learn more about early solar system bodies. ESA's Hera mission, launched in 2024, will study the Didymos asteroid system. These are 2 asteroids that were the target of NASA's DART mission in 2022. Hera will map the craters created by DART's impact and analyze Didymos' regolith. The most exciting future mission for astrobiologists is NASA's NISA mission, set to launch in 2030. NISA will visit 2 asteroids, a carbonaceous chondrite like Bennu, and a silicate asteroid. It will return samples from both, allowing scientists to compare their organic and water content. NISA will take what we learned from Bennu and Rygu to the next level, Dr. Keller said. We'll study 2 different types of asteroids and see how their organic matter differs. This will help us understand how life's building blocks formed in different parts of the solar system. The Bennu sample has given us a new perspective on our place in the universe. We are not just inhabitants of Earth, we are products of the solar system. The water in our bodies, the proteins in our cells, the DNA that makes us who we are all may have come from asteroids like Bennu, delivered to Earth 4.5 billion years ago. This discovery changes how we think about life, Dr. Loretta said. It tells us that life's building blocks are common in the solar system and probably in the universe. If life started on Earth because of an asteroid, it could have started on other planets too: Mars, Europa, Enceladus. We're not alone in the cosmos in more ways than one. As we continue to explore asteroids and other bodies in the solar system, we may find even more evidence of life's cosmic origins. But for now, the Bennu sample is a reminder that we are all cosmic children born from the dust of asteroids, water from ancient oceans, and the building blocks of life from the stars.